Hello friends, in this lecture we are going to see how we can design a binary counter that repeats its count every 5 counts. And we are going to design this, then test our results in multisim, which is a simulator that we are going to use in this particular video. Now let's look at this statement, designing a counter that repeats its count every 5 counts. We are going to take a basic counter that starts from 0 and then increments the count by 1, increments the count by 1. So if it is from 0, it will be 0, you go to 1, you go to 2, you go to 3, you go to 4. Since we are looking at 5 counts, then this is going to be 0, 1, 2, 3, 4. So it will be 1, 2, 3, 4, 5. So it will stop at 5. So now, if we are looking at 5 states, we have a formula that we are going to use in designing so that we know how many, for example, flip-flops do I need. So I know that 2 to power n should be greater than or equal to capital N, whereby capital N is the number of states or number of counts, then n is the number of flip-flops. Okay? Small n is the number of flip-flops. Now, if we are looking at the states of 5, so that means 2 to power n should be greater than or equal to 5. So we are going to look at uh, what can be our least value of n, the minimum value of n, that will give us a value equal or greater than 5. So the least we can get is n equal to 3, because 2 to power 3 is greater than 5. So this would mean you have 8. So if you have 8, that means we are going to use 3 flip-flops. So in everything we are going to do for us to achieve this target of a counter that repeats its count every 5 counts, we are going to be looking at 3 flip-flops. And now the type of flip-flops we are going to use in this design, we are going to use a D flip-flop. So what is a D flip-flop? One, what we know about it is a single input flip-flop. The input is D. Then we are going to use the one that has a set and reset. Then we are also going to use a rising edge trigger mechanism. A rising edge trigger mechanism, we mean that the signal supplied at the clock is going to be, we are going to have high and low, high and low, high and low. So this is going to make it an up counter. Okay, so we are going to look at an up counter, since we have a rising edge trigger mechanism, and obviously you see when you're moving from low to high, then you're talking about what? You're talking about an up counter. That is from 0 to 4. This is an up counter. A down counter would be from 4 to 0. And this would be achieved by using a falling edge trigger mechanism. So what else do we need here? We have seen that we need 3 flip-flops, and we are going to use a D flip-flop. So what are we going to have as our outputs? Outputs are going to be 2 2, since we are talking about 3 bits, we are going to have choose 2, choose 1, choose not in that order. This one being the most significant bit and this being the least significant bit. So that is 3 bits. Then it means also we are going to be looking at the during the process of designing, we are going to look at a number of things. So I had already earlier on solved this problem. I'm just going to right away throw through the design. Then we rush to our multisim and be able to simulate this. So this is our state diagram. First of all, you need to have your state diagram that shows that this is a 3-bit synchronous counter running out from 0 to 1 to 2 to 3 to 4 and finally back to 0 and to repeat like that, like that, like that. This is 0, sorry. We are saying that this is 0, this is 1, this is 2, this is 3, this is 4, and it goes back to 0. Okay, we go to excitation table. The excitation table tells us how a D flip-flop is going to behave when we have a low and the high states at the present state and the next state. So true of T is the present state, and then true T plus 1 is the next state. Now, if we have a 0 and if we have a 0 at the current state and we want the a low or a 0 at the next state, then we have to put 0 to the input at D. If we have a high state at the current state and we have to get a high at the next state, then we need to supply a high or a logic 1 to the D input of the flip-flop. So generally, you will see that D always takes the state of 2 T plus 1 or 2 plus. So you'll see that when you have 2 plus being 0, you have D taking 0. If it is 1, D is going to take a 1. If it is 0, it will take a 0. If it is 1, it will take a 1. So we go to the states table. The state table is also like this. You write your present state, you write your next state, and the flip-flop inputs. Then later on, you need to draw the K-maps or the Karnaugh maps for each input, that is D2, input D1, input D0. Then later on, draw the logic diagram. So this was earlier on done. I'm going to share the link to that video and you'll be able to flow through and follow and be able to design this counter. So let's go to multisim. So in our multisim, I've already imported these components. If, for example, I look at this design required an XOR gate, an AND gate that requires 2 inputs, an AND gate that requires 2 inputs, and an AND gate that requires 3 inputs. Then you also need a D flip-flop. Then you need a DCD hex for displaying your output. And then you also need a clock signal. A clock signal is here. This is a clock signal. And we are going to use a plus 5 volts and at 1 hertz. If it is if the frequency is high, then it will be disturbing us to read the output. So let's go and see how to import these components. So if I want, for example, I want a D flip-flop, I go to pressing components. I go to this bar, then I press components. When I reach here, I look at all families. I need all groups and all families. So what I do, I put here on my search, and put D flip. I need a D flip flop, a D flip flop. The one which has a positive clock. Ah, if I wanted the one with a negative clock, I would take the other one, but let me take this. So if I take this, I click, it will come. And obviously, I already have it, so I'll just delete that. Then I go back and look for what? Look for the DCD hex. DCD hex is there. I take it. Then I need to look for the XOR gate. XOR gate that requires two inputs. I take it. I need maybe the AND gate for two inputs. I take it. For three inputs, I also take it. So I press everything that I need here. The same thing with these probes to indicate my output with this clock signal, and then put them here in my environment, then start on the connection. So now I'll go back to my design and see that the output D1 required that you have true inverse, then true 1 XOR true not. So that means I will have my two inputs going to an XOR gate, then its output is going to go to an AND gate, then also with the true 2 inverse going to AND gate, and all so the output of the AND gate will go to D1. So I'll go to here, you go to D1, my D1 is actually here. So I'll have my AND gate that is receiving XOR. This XOR gate is receiving a true, we say the true not and true one. So this is the one, this is a not, this is a 1, this is 2. So I will come here, I will come here, I will come here and bring my input. Then I go to true not. I also bring my input to this XOR. So its output goes to the AND. Then the other AND input comes from the true to inverse. So true to inverse, true to inverse is here. Okay, I have finished that. The input, that was the input D1. So I can go to input maybe D note. D2 has an AND gate with three inputs. So AND gate with three inputs, true 1, true not, and true 2 inverse. So I got true 2, I have true not, true 1, and true 2 inverse. So I pick my output here, my input here, and take it to true 2 inverse. So that's true 2 inverse has completed the connection for the three input AND gate going to D2. So I'm remaining with now D note, signals to D note, signals to D note. Let's look at what is D note. D note is receiving two inputs to the AND, then that AND is taking it to D note, of course. So we have true to inverse and true not inverse that are going to the AND gate. So we have the AND gate that is receiving 1, 2, 2 inverse, and then we are told, or we have discovered that it is also receiving true not inverse. And then this output is going to D note. Now what remains is connecting our clock signal. This clock signal is going to be what we are going to call simultaneous connection to each clock. So in other words, I'll pick from this, I go to the main, and from here still I'll connect to the main. Then what remains is connecting my outputs to the true note, the true one, and the true two. So true two, we want our values to be, uh, for example, the most significant bit should be here. Then the least significant bit should be there. So since this is a true note, true one, true two, my most significant bit is going to be coming from here. So I'll pick most significant bit is coming from Q2, and then I also want to have a copy of that by using a probe. Then this one will obviously go to Q1, and this one will go to Q0. Then this one will go to this Q1. Then this one will go to this tunnel. So it is time for me to simulate this problem. So let me simulate. Okay, you can see it's counting from 0, 1, 2, 3, 4. It goes back to 0 and on and on and on and on and on. So until you stop it, that's when it will do what? It will stop. So when I pause it there, you see it is at 3, and this is obviously 0, 1, 1. When I continue it and stop at 1, you see it is 0, 0, 1. So this is how we can simulate our binary counter that is counting from 0 to 4, that is 5 counts, and then repeats after 5 counts in multisim. And then we have also looked at how you can design it step by step. So be encouraged to share, like this video, and also put comments in case you don't understand anything. We shall be available to get back to you and make all things clear. Thank you so much.